Hello, everybody. Today we're going to talk about molecular geometry. So first thing you need to do is go onto Canvas, get to our molecular geometry data sheet, open it up. All right, and we're here. Okay, so on this data sheet, there's might be some information that you guys haven't talked about in lecture. I'll quickly kind of talk about what those symbols mean. Okay, but really what we're going to do is we're going to pick 4 molecules and we're going to build those 4 molecules and learn how to kind of accurately predict their 2-dimensional shape and their 3-dimensional shape. Okay, so we've got a list of 70 different molecules that we can choose from. All right, so I'll grab a couple of these to work through. Okay, we'll talk about what hybridization means. All right, and these are lists of potential shapes. Right, so we'll have to name them. Okay, to combine that information together, right? The types of shapes, this hybridization, which I'll talk about. Okay, there's also another just way that we can express this information to then also identify the names of those compounds. All right, so this is just a resource. Ultimately, what you're going to do is you're going to turn in this data sheet right here. All right, so the only thing that I'm looking for, there's no report, there's no pictures that you need to make, except for you just need to complete this. Okay, so first, we just need to understand what is molecular geometries, how can we predict them, and then we'll just kind of go from there. All right, so let's learn how to predict the shape of a molecule. All right, to do that, all right, we do need access to a periodic table because we got to figure out something about a periodic table. Okay, but to predict molecular geometries, we basically just need to understand how molecules are formed and how we stick atoms together. All right, to do that, we need to make what are called Lewis structures. All right, a Lewis structure is a 2-dimensional representation, right? So it's a 2-dimensional shape of our molecules. All right, to do this, all right, I'm just going to break it up into individual steps. Okay, there's a series of rules we follow. Okay, so I'll walk through an example real quick, but as I'm introducing the steps, I'll also walk through the process that we need to know and kind of the understanding we need to have to then connect our atoms together. All right, the first thing that we need to do when we're trying to draw a molecule is we're going to sum all of our valence electrons. Okay, the question might be, what are valence electrons? All right, so if you haven't gotten there in class yet, okay, our valence electrons, right, they are the s and p electrons after your noble gas. All right, so you all remember that if you're looking at the periodic table, all right, you've got your s electrons right here, and you've got your p electrons right here. Okay, so when we're trying to find valence electrons, it's really not intended to be tricky. We don't care about d electrons, and we don't care about f electrons. All right, we only care about s's and p's. All right, because those are the electrons that are going to interact to make bonds. Okay, so let's just do an example. Let's say I wanted to find the number of valence electrons for carbon. Okay, all we have to do to figure that out, like how many s and p electrons it has after a noble gas, you simply start on the left-hand side of the periodic table and then count over, right? 1, 2, 3, 4. All right, carbon's got 4. Right, if carbon has 4, nitrogen would have 5, right? And we're counting electrons. All right, so one thing to notice is that, all right, there's really a trend. Group 1's 1, group 2 is 2, 3, 4, 5, 6, 7, and 8. All right, there's actually an old style that's listed on this periodic table, which actually encodes that information. So the Roman numerals 3, 4, 5, 6, 7 actually tell you how many valence electrons you have. All right, but we're not going to worry about that. We're just going to use these groups as our example. Okay, to do this, let's just pick a molecule, right? So the first molecule I'm going to do is H2O, right? So you're all going to have this as your first one as well. All right, I need to add up all my valence electrons. All right, so if I've got H2O, I've got 2 hydrogens and I have an oxygen. All right, if I'm trying to figure out how many I've got, well, hydrogen's got 1, right? Counting over, it's got 1. So that's 2 times 1. Okay, plus my oxygen right? So if I continued from my carbon, carbon's 4, nitrogen's 5, oxygen's 6. All right, so this is the total number of electrons I have to distribute. All right, so we're going to use those to kind of build our structures. All right, step 2 is we're going to make a single bond between our central atoms and the surrounding atoms. All right, this is maybe new terminology that we haven't talked about yet. All right, so if you haven't talked about it, not a big deal. That's why we're going through it today. All right, we want single bonds. We want to talk about central atoms. We want to talk about surrounding atoms. Okay, when we're talking about bonds, bonds are a way that we represent atoms interacting with each other. Okay, if we have ionic compounds, okay, they're just ions sticking together, so positive charges and negative charges. So we're not talking about that. We're talking about what are called covalent bonds. All right, so a covalent bond is the sharing of electrons. All right, so if I have a single covalent bond, it means that I can represent it like this. So I've got 2 atoms. Okay, and that line actually represents a pair of electrons, all right, because we're always going to put things down in pairs, right? So electrons have to be balanced in pairs. If you have a single electron, that's a radical. We're not talking about radicals. All right, we got a single bond, we've got a double bond. So if I had 2 atoms connected like this, or I'd have 2 pairs of electrons next to them. All right, so paying attention to how many electrons we're doing. All right, if I've got a triple bond, that's X with 3 things attached to it. Or I have 6 electrons. All right, so that's a lot of electrons. Okay, most things are going to be single bonds. All right, there's an example where we'll probably see a double bond somewhere. Okay, but we just need to be able to work through this and be able to keep track and basically count how many electrons we've got. Okay, well, what does central atom and surrounding atom mean? Okay, well, our assumption is when we're drawing our pictures is that we've got an atom in the middle and then everything else is connected to it. Okay, so if I have a molecule like this, if I've got AX4, right, our assumption is that whatever is written first or is the least abundant, all right, we've got a central atom, which means we've got A. All right, everything else is going to be connected to A. So in this example, I've got these 4 different X's, so whatever generic atoms they are, and those X's would be called my surrounding atoms. All right, in this example, right, the central atom is either written first or it's the least abundant. All right, so in H2O, oxygen is my least abundant, and I'm connect those 2 hydrogens together. All right, so my central atom connects, or my molecules connected by a center, right? So in this example, I've got oxygen in my center. All right, after each step, so I stop, I count my electrons, and I check for octets. Okay, what you may have learned is that octets are 8 electrons. All right, that represents noble gases, right? And noble gases are very stable. So atoms and molecules want to have octets, right? So they want to see 8 electrons. All right, there's one exception to that. All right, that one exception is that hydrogen, it only wants 2, right? It only wants 2 electrons because helium only has 2. Okay, so when we're checking octets, we just need to make sure that we're distributing all of our electrons and that the atoms that we've got, or the molecules that we've got, also see 8 electrons. All those atoms see 8 electrons, except for hydrogen, and hydrogen's happy with 2. All right, so I made my single bond. I stop, I count, right? On the board, remember, a single bond equals a pair of electrons. So I only have 4 electrons on the board right now. So I need some more rules to do this. All right, rule number 3, complete octets around the central atom Okay, starting with the surrounding atoms. All right, so I need to distribute my electrons. Okay, if I can accept any more electrons, they go on the outside. In this example, right, this hydrogen, if it's looking around, it sees 2 electrons. It doesn't want any more. All right, this hydrogen looks around. It sees 2 electrons. It doesn't want any more. All right, so these are kind of like Venn diagrams where they're going to overlap. Okay, my oxygen looks around. It sees 4 electrons. All right, it needs more electrons. All right, we're going to figure out how we can do that and how we can complete those octets. Okay, so we're going to start making octets. All right, we're going to start with the surrounding atoms. So we start on the outside in. Okay, if those surrounding atoms don't need electrons, all right, any leftover electrons we've got, all right, they go on the central atom. All right, so in this case, I've got 4 electrons on the board. All right, I've got 8 total, so I've got 4 more left over. All right, those 4 more left over go down in pairs. All right, this pair of electrons, so lines are called bonds. These pairs of electrons are called lone pair. All right, they're also called non-bonding electrons. Okay, but the most important aspect of them is that they don't participate in bonding. All right, they're just hanging out. Okay, so this is my valid Lewis structure for water. Check. Okay, this is my Lewis structure. All right, that's 2-dimensional. All right, you're 3-dimensional because the molecules you're made of are 3-dimensional. All right, so we got to figure out what's happening in 3 dimensions. All right, step 5. Okay, I'm going to add this, but we're not using it because water's already done. But if our central atom still needs an octet, all right, we're going to try multiple bonds. All right, so I'm going to do 2, right? I'm going to do water and I'm going to do a different one. And I want to make sure that you understand where I'm going with water, make sure you understand where I'm going with the second one. And these last 2, I'm going to provide to you that you need to do on your own. All right, so we'll talk about Rule 5 in a second. All right, but if I need to figure out my 3 dimensions, okay, that's called VSEPR. All right, Lewis structure gets us 2 dimensions. VSEPR gets us 3 dimensions. All right, those 3-dimensional shapes are shown in your diagrams on your data sheet. Okay, but in general, what VSEPR means, it stands for valence shell electron pair repulsion. Okay, and what electrons do is electrons are just little magnets, right? So little magnets, if you have the opposite ends of a magnet, or if you have the same end of a magnet and try to put opposite magnets together, so negative and negative, they push each other away. All right, so electron pairs, they're bonds. All right, they're lone pair electrons, they're non-bonding electrons, or they could just be bonds themselves. All right, and these are all called electron domains. Right, otherwise expressed ED. Okay, and the theory is that if you've got a bunch of electrons around a central atom, right, they push each other away as far apart as possible. All right, so they repel each other. That's what this repulsion means. Not repulsion, repulsion. Okay, right. And the important point is it's around the central atom. Okay, what I like to do is I like to just think about some examples. So let's say I got this molecule. And my central atom is like a table. Okay, if I've got 2 things around that central atom, for those 2 things to be as far away from each other as possible, all right, so those magnets are pushing each other away so that they're as far away from each other as possible. All right, those 2 things would be on opposite sides of the table. All right, which means that I have a molecule that looks like this. All right, so this distance would be 180 degrees. The name of this shape would be linear. And this example is for any central atom that sees 2 electron domains. All right, so if it sees 2 things around it, it's going to feel like a linear molecule. All right, let's say I've got three things around it. Okay, I've got a table. Got these three regions of electrons. Okay, pushing those around the table. I've got my table. To be as far away from each other as possible, they'd be on the corners of a triangle. So the way that would look, I'd have A, I'd have X, I'd have X, and I'd have X. Okay, those would be about 120 degrees away from each other. And the name of this shape, right? So this shape is still flat. All right, we're talking about three dimensions. So far, everything is planar. All right, it looks like a triangle, so it's trigonal, but it's flat, so it's planar. All right, so this is a trigonal planar molecule. Okay, if this has three electron domains, but remember, those three electron domains, they could be anything. They could be bonds, they could be lone pair electrons. All right, so another type of shape that we could see is if instead of bonds, we had a pair of electrons. All right, if we had a pair of electrons on top, okay, there's still three electron domains. Okay, they're still pushing each other away. All right, but the thing with electrons, you can't see electrons. All right, so since you can't see electrons, what that object looks like, it doesn't look like a triangle anymore. Now it looks like a boomerang, right? And this is called bent, right? It's called bent or angular. All right, the last type, there are lots of types listed on our data sheet. All right, you're just going to choose up to this shape, which is called a tetrahedral, or because that's the most biologically relevant. Those are the most common types you're going to see in the future. All right, but if I've got four things around me, so 1, 2, 3, and 4. Okay, for those four things around, I've got to think in three dimensions. All right, so it's not just a square around a table. Right now, all right, that table, I can put my three objects around my table. Okay, but for them to be as far away from each other as possible, one of them needs to be on the top or the bottom. All right, and this object is in 3D. So we got to draw a picture in 3D. All right, so if I've got four electron domains, all right, I got to think in three dimensions. All right, to do that, okay, we draw two of these with a line. So those means that it's planar. It's in the plane of the screen. Okay, one of them is coming towards you, right? This is called a projection. So this is towards. And one of them is going away from you. So there's this dashed line, right? And that means away. All right, this shape is called a tetrahedral. All right, we're going to figure out what type of shape water is in a second, but we just had to introduce these. All right, there's two derivatives that we can find. If I've got one pair of electrons, I got my X, and I got my another X. All right, so looking from the top, so it's really hard to kind of wrap your brain around this, but if you have a little model kit, that would be helpful. All right, looking from the top, all right, this looks like a triangle. All right, so it's trigonal. All right, but it's a triangle that's not flat. So this is called a trigonal pyramid. All right, the last type that feels like a tetrahedral, you got two of them in the plane. So those electrons are in the plane. You got X, you got another X. Okay, this shape, right? Hard to imagine what it looks like. You got something coming towards you, something coming away from you. If I rotate it, so I'm just going to rotate this a little bit and just draw it like this instead. All right, that's exactly the same thing. And that molecule is called bent. Okay, these shapes are provided for you, right? I went through the logic to try to explain to you where they come from. All right, but if you look at your data sheet, okay, you'll see these shapes and you'll see the name of these shapes. All right, so you'll see linear, you'll see trigonal planar, you'll see tetrahedral, right? These are the three shapes that I'm going to kind of choose for you. You're not going to have to worry about these other shapes. All right, but one way to do this is, okay, how many bonding electron domains does it have? All right, if it has two, it's linear. That's what we figured out. If it's got three, we call it trigonal planar. If it's got four, we call it a tetrahedral. So you can use this diagram or this table to kind of predict what your molecules are going to look like. Okay, here's those pictures too. So linear, trigonal planar, bent, tetrahedral, trigonal pyramid, bent. All right, so you got these shapes right here. Okay, now let's talk about what this means. All right, what does this hybridization mean? Okay, we don't have to go into it really in any detail at all. Okay, but hybridization is about how those electrons interact with each other and what kind of mathematical shapes they can make. Okay, you don't need to know this to be successful in lab, but I do just want to introduce it to you real quick. All right, so these are called hybrid orbitals. And they're called hybrid orbitals because some shapes are combinations of more than just S's and P's, right? Sometimes you got some D electrons. All right, but basically, if our electron looks like an S, and we combine it with an electron that looks like a P, right, and they're overlapping each other, okay, what it turns into this hybrid orbital, right? It turns into an SP of some sort. All right, this is math. This is a bunch of fancy math. Okay, there is a series of different types of shapes, right? So there's different combinations of S's and P's and D's. All right, so if you're SP, if you're SP2, if you're SP3, if you're DSP3, or if you're D2SP3, what that's telling you, it's telling you the shape, but it's also telling you how many things can connect to your central atom. All right, so this is really all about your central atom and how many things are connected to it. All right, an SP, one easiest way to think about this. All right, look at your exponents. All right, if my exponents are 1 plus 1, that means that I can connect to 2 things. So I've got 2 electron domains. Well, what about this? If I'm 1 plus 2, that means I've got 3 electron domains. If I'm 1 plus 3, that means I've got 4 electron domains. Well, what's it called if you got 2, 3, and 4? This is linear. This is trigonal planar. And this is a tetrahedral. Okay, so that's all that it is. The D gets you into these higher, kind of more complicated shapes. But again, we don't need to worry about that. Okay, so to do this VSEPR, to do this analysis, okay, what we need to do is we need to figure out, okay, not only what our molecules look like in 2 dimensions, so we're VSEPR, but we need to look at our central atom. Okay, so to do this, to ultimately predict our shapes of our molecules. All right, step 1 is we need a valid Lewis structure. And step 2, we need to push our electron domains around the central atom. All right, we're going to push them as far away from each other as possible. All right, so if I've got this, I've got my valid Lewis structure. Okay, first thing I do is count my electron domains. All right, so oxygen sees how many electron domains. All right, so electron domains are bonds and their electrons, right? They're pulling each other, pushing each other away. So if I'm just counting, right, I'm just counting single bonds, double bonds, triple bonds, whatever, pairs of electrons. All right, it sees 4 things. Okay, what's it called when you see 4 things? What's your shape going to be? Well, if you see 4 things around your central atom, all right, those 4 electron domains, it means you're going to feel like a tetrahedral. All right, so water feels like a tetrahedral. Okay, so let's look at our little sheet right here. Okay, how many electron domains does it see? It sees 4. What's the name of the geometry that's got 4 electron domains? Right, that's called a tetrahedral. Okay, but we don't have a tetrahedral because we don't have 4 atoms. Right, this object or this molecule has got 2 pairs of electrons. Right, and we can't see electrons. All right, so what's a tetrahedral that's got 2 pairs of electrons? What's that called? Well, we figured that out, right? So if I've got a tetrahedral, it's got 2 pairs of electrons. Right, we call that bent. And if I was going to draw it, all right, since I'm doing this for you, okay, show me with the projections. All right, show me that you got hydrogens coming towards you, you got a hydrogen going away from you, and you got those pair of electrons. So that's the geometry of it. Okay, we're going to do one more. All right, this is going to help us also think about multiple bonds. All right, so we're going to do CO3 2 minus. Okay, so if I'm doing carbonate, first thing I got to do, sum up all my valence electrons. All right, carbon, 3 oxygens plus 2 electrons from my charge. Okay, carbon's 4, each oxygen is 6. All right, plus 2, that's 18, 20, that's 24 valence electrons. All right, make my Lewis structure. Okay, I'm going to draw this. All right, so I'm going to go through all my rules, make my single bonds, make my octets around the outside. All right, so around my central atom. Okay, I stop, I count my electrons. Right, in this case, I only put down, or I put down all of my electrons. It's 8 times 3, that's 24 electrons. I don't have any more to put down. Okay, so if I go to my rules up here, I completed my octets. I don't have any leftover electrons. So that's when I have to do step 5. All right, so you have to do step 5 if you need to. I need to try multiple bonds. I need to share electrons. Okay, the atoms that share electrons are typically surrounding atoms, right? So I've got a bunch of these dots around oxygen, right? If I want to share them, I can simply draw them, between those two atoms, right? You are drawing the picture, so don't feel uncomfortable about changing it, right there. Okay, checking my octets, oxygen looks around, it's got an octet. That oxygen, the other oxygens have octets. Carbon looks around, sees 2, 4, 6, 8, right? Everything's great. All right, there is one other thing you need to do with a molecule that has a charge. Just make sure you use brackets. All right, if it's an ion. All right, so you got your brackets and you put your charge on top. Okay, when carbon looks around, right, carbon's our central atom. How many things does it see? It sees 3, right? It sees 1, 2, 3. It sees 3 electron domains. Okay, the question is, what's the geometry for 3 electron domains? Again, we figure this out, right? So if I have 3 electron domains and I push them around, right, it looks like a triangle. So it's called trigonal planar. Okay, the name of the molecular geometry. Well, in this example, there are no lone pairs on my carbon. Okay, so that molecule is just going to be trigonal planar. All right, because there aren't any things I can't see. And to sketch the geometry, do your best to draw it looking like a triangle. Okay, this isn't an art class, so don't worry about perfection. Okay, but just try to show me that there is some relative angle between them. Okay, now we got to do some other ones. All right, these are what I want you to work on. Okay, so work together, reach out to me if you need any help with them. All right, we've done 2 of them. Okay, but the other 2 that I want you to do, I want you to do NH3. Okay, I also want you to do OF2. Okay, so getting through these, all right, again, if you need help, reach out to me. Just see me in class, send me an email. All right, show me work so that I can help you. All right, but otherwise, once you've completed this table, all right, also include the stuff that we did together. Okay, take a picture of it, submit it up on Canvas, and then you're good to go. All right, please just let me know if you have any questions. Thanks and have a good day.